Okay, welcome back. So we're kind of sort of finished with the minimum spanning tree thing, and we're ready to move on to the next topic, which is the shortest path algorithm. So one more time, an MST basically means I must be able to connect to everybody, okay? And with the collective path, the sum of all the edges is the shortest, okay? That is not the same thing as charting a path from A to B through an entire graphic. Okay, that is not at all what we're talking about. So, shortest path is just like your GPS thing. I'm in Dallas and I need to go to San Francisco. Chart me the shortest path. Cool. All right. So I have no need to visit every node, right? I mean, both the traversal and the MST hit every single node. Well, my God, when I'm trying to go from Dallas to San Francisco, I do not want to stop in every city. Okay, good. I'm glad you guys have got this. Now, MST won't actually work here because of its greedy part. So let me explain what I mean by this. It's a really cool example. So let's say this is a ring. Now, if we were using an MST approach, if I wanted to go from greedy would say, well, I have a choice between 1 and 2. I'm going to take 1. And then, I'll take 1, I'll take 1, I'll take 1, I'll take 1 to go. So with its way of thinking, using just the MST approach, the shortest distance between A and B is this route. So clearly that is not going to work for us here. So we cannot use MST to attain a shortest path, because clearly the shortest path is between A and B is 2, not 1, 2, 3, 4, 5. Okay? Good. So the greedy algorithm here will not provide you with the correct answer. Okay, just saying. All right. So there's yet another Dijkstra's algorithm. Hey, this guy's been in the business for a while, huh? And basically, it is a modification of the MST. It is. To consider fringe nodes. So is it still greedy? Well, it is just parts of it are. It starts off being greedy, and then it has the ability to backtrack a little better than just a plain old MST. So yes, it's still greedy, but not as greedy. Those are horrible descriptors, but you kind of get the point. So again, consider a maze. If I'm down here and I made this entire trip through the maze, and then finally I realized, man, that was the wrong decision. I need to get the heck back. So I'm not just backtracking 1. I'm backtracking, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now I need to go off in this direction. So its ability to backtrack further, maybe, is a way of describing it. So it's greedy with a longer memory. I don't know. Kind of a weird way of looking at it. Okay, so Dijkstra's algorithm. Again, there's some extraordinarily pseudo code. Ha ha ha. Some pseudo code. Whoops. That basically says start a node, build a fringe. Okay, so that's useless to me. Now let's look at it from the point of view of this guy. So this was the original example they use on figure 8.8a. Okay. And so I pick a node and then go through this thing and then go through this thing and just keep going, right? That's kind of sort of the way the MST thing worked. Except here I just have longer memory and I can figure it out as I go along. So one more time, just the narrative on how it works. Pick a node that's not already been picked because I don't want to visit anything twice. Add that node to a tree. Recalculate the distance of all of its adjacent paths. Get the sum of that so far. And then keep or toss whichever ones you don't need. Okay, that's basically how it works. So once again, we're going to go to Geeks for Geeks. And here's the Dijkstra's shortest path algorithm. And so once again, they don't have it in all the languages, so I apologize, but you'll be able to figure it out, I would imagine. So basically, get the minimum distance, and then we go through and do this thing. Okay, just saying, this is not actually all that bad. I think you could probably convert this to other languages without too much trouble. Okay, so one more time. What's the point here for shortest path? The shortest path is I want to get from A to G. What's the shortest path from A to G? Okay? That's kind of what I want to know. I don't care about visiting everybody. That's not what I'm after. I just want to get from A to G. That's it. Nothing else. Good. On page 258, they talk about a bi-connected component algorithm. So basically, this is back to that thing about fault tolerant. So here is an example of a connected graph, okay? But if you kind of look at this for a minute, you can kind of sort of tell that there's a weak link in the chain. In other words, if node C failed, I'd still be able to get to every node. But if node D failed, I would not be able to get to all of them. And likewise with H. If H failed, I would not be able to get to all of them. So the bi-connected component is really the search for the weakest link. Okay? Now, these guys are mathematicians and they're producing, PhD dissertations. So heaven forbid they would call it a weakest link. No, they call it an articulation point. Of course they would call it that. So, normally, let's just assume in a bi-connected kind of a scenario, there's at least two paths to get to every node. That's what bi-connected means. At least two paths. So that means it's fault tolerant, right? So, there's a cool story. I guess I'll tell you guys a story. Back in the Cold War, the idea was we couldn't have our communications system so that, if somebody nuked, Dallas, that the messages couldn't go from New York to San Francisco anymore. So they wanted to make it so everything was fault tolerant. And so there was multiple paths to be able to get to things. That's how the internet was born, out of the paranoia of having a disruptive communication system that could automatically route around a dead node. You didn't have to go, oh wait, let me go throw a switch manually. It was designed so the minimum spanning tree would remap itself and just map the traffic around. Okay, that's how all this started. The internet was born out of Cold War paranoia. Okay, now, back to the story. So, this bi-connected component thing basically says, I need to find the weakest link. So if the internet hub went down, I'd still be able to get things. So our articulation point is that place, okay? So there's a brute force approach. The brute force approach would be, go pull every single one at a time. Pull a node and then run just a traversal. Do you get to everybody? Yes or no? I pull A and I run the traversal. I pull B and I run the traversal. I pull C, run the traversal. Okay, that would have a big O of, node n times whatever, however long it took to get to the traversal part, right? So that would be not all that great as far as that. It's kind of a silly approach to the brute force. So there's a better technique. Using a depth first. Now, can you kind of imagine why we're using depth first versus breadth first? Because I'm trying to get from point A to point B, right? I'm trying to find the edge. I'm trying to find the node. So it kind of makes sense. Can you kind of visualize that doing depth first would be the most appropriate type of traversal to be able to get here? Maybe just by looking at it, going, yeah, I want to be able to get to D rather quickly. Okay, I don't want to spend an awful lot of time. I want to be able to get to D rather quickly. And so depth first will get you there, get you to D or H rather quickly. Okay, here's how it works. So I keep count of each node, all right? I store an index, like each one of the nodes, and then use the smaller index to back up. If it's greater than or equal to the current index, then we found a bi-connected. There's a figure here, and it's kind of, that. This is what it's going to look like when we're kind of sort of done. Okay? So, there's no pseudocode here. It's just a description of how you would go about doing this, trying to find these guys. Use the smallest index. So, if I got to the point where if it's greater than equal to the current index, then I've found a biconnected component. So if I can get to here and there, and there's two different ones, I know, okay, there's two different ways to get there. That's what we're after. Is it biconnected? Okay. Alrighty. So that's how this thing gets broken up. These are the biconnected components. These are all biconnected. These are all biconnected, and that, I guess you could consider that biconnected. But anyway, you got it. All right, there's only one more thing left to do here in this particular part of the chapter, and that is talking about partitioning sets. So partitioning sets is the ability to break a graph into smaller chunks. So let's go find us a graph to look at. So let's look at this guy. Okay, so figure 8a graph. And I need to break that up into chunks and then be able to reassemble it. So you might think, what on earth is the use case for this? Well, to tell you the truth, it's actually pretty doggone easy to wrap your head around. Instead of me driving from here to San Francisco, perhaps I wanted to stop in Denver. Okay, so minimum spanning tree, right? That's not going to work for me because it's just going to build a map. Shortest path doesn't have a technique for intermediate stops. So you use partitioning. I break up this chunk of the map and say I want the shortest path between Dallas and Denver, and then I break up this chunk and say I want the shortest path from Denver to San Francisco, and then you put them together, and now you have intermediate steps. Shortest path can't do it, but shortest path with partitioning sets will. Okay, so that's how your GPS works as well. If you told your GPS, well, maybe not. Maybe Google Maps. You're trying to do a route for Google Maps, and I want to go from here, but I do want to stop here, like overnight. I have a motel reservation here and a motel reservation here, so I'm not going to drive across the entire United States in one day. I'm going to do it in 3 days. So I need to be able to stop here and stop here and stop there. Got it? Good. Okay. So how does this thing work? Well, you create an array of parent nodes. So an array of parent nodes. And so you broke this thing up, and each one of these guys like 5. The -7 means that's the number of nodes that are below me. That's my number of children. Okay, like that. Okay, so for example, 7 has no children. 9 has no children. 12 has no children. But 3 has 5? Okay. Oh yeah, 5 as its parent. Got it. All right. So that's how that part works. You assign them all, start off with a -1, and then you just go through it, and all the negative numbers are the roots of the partition. So after the roots, which ones are the roots? Well, it looks like 6 is a root, 5 is a root, and 11 is a root. So it very easily lets me to break these guys apart, and break them apart in such a way that you don't, like slice a map so that you can't get from point A to point B. That's kind of important too. When you partition these things, you got to do it carefully so that you can stitch the things back together. You just can't really take a pair of scissors and go, because you may end up with one of those things where you cut off something so it's impossible to get to there because you cut it off. So your partitioning has to be scientifically done. Okay, so that figure 811 on page 262 basically shows how it's done. It talks about who's the parent, and then negative numbers means I don't have any parents, or it's the number of nodes below me, kind of a thing. Okay, is that kind of making sense? All right, this was kind of a short chapter, and the pseudocode was practically useless. So you do have to go out to the internet to be able to do these things, for example, like in a homework assignment. Okay, we are done with this chapter, and I'll see you guys again in the next chapter.